Welcome to RenEnergy.com, your renewable energy and sustainability platform. At RenEnergy.com, we believe in the power of clean, sustainable energy to transform the way we live and work. That's why we offer a range of solutions for businesses and homeowners looking to switch to renewable energy sources such as solar, wind, and water. Hello and welcome to RenEnergy.com's channel, your hub for cutting-edge energy solutions. Today, we're diving into how we can revolutionize green hydrogen feasibility studies by integrating machine learning and data science. Stay tuned to discover how these technologies can enhance the sustainability and efficiency of green hydrogen projects. Section 1. Data collection and management in the realm of green hydrogen feasibility studies. The foundation of our approach lies in robust data collection and management. By gathering extensive data from diverse sources such as weather stations, renewable energy outputs, and market trends, we ensure a comprehensive dataset for analysis. Managing this data effectively is crucial, as it feeds into our machine learning models and predictive analyses. The significance of this phase cannot be overstated. For instance, data from weather stations helps in predicting the availability of solar and wind energy, which are critical for green hydrogen production through electrolysis. Similarly, understanding market trends aids in forecasting the demand and price dynamics of green hydrogen, influencing project viability. In the context of data science, we employ advanced data management systems that allow for efficient storage, processing, and retrieval of this vast array of data. This not only streamlines the workflow but also ensures the integrity and quality of the data being used. Moreover, we integrate data from environmental studies to assess the potential impacts of green hydrogen projects on local ecosystems. This holistic approach to data management sets the stage for more accurate and reliable feasibility studies, underpinning the entire project lifecycle from conceptualization to implementation. To sum up, in this initial phase, our focus is on establishing a strong data foundation, which is critical for the subsequent application of machine learning and predictive analytics in green hydrogen projects. This approach not only enhances the accuracy of our feasibility studies but also contributes to the sustainability and economic viability of green hydrogen as a renewable energy resource. Section 2. Machine Learning and Renewable Energy Forecasting. As we delve deeper into the integration of machine learning and green hydrogen feasibility studies, we find that one of the most critical applications is in forecasting renewable energy output. Renewable energy, particularly solar and wind, plays a pivotal role in green hydrogen production. The use of machine learning models here is not just innovative but essential for accurate predictions. Let's start by understanding the challenge at hand. The production of green hydrogen through electrolysis requires a consistent and ample supply of electricity, which in our case, is derived from renewable sources. However, the inherent variability of solar and wind energy can pose significant challenges. This is where machine learning models become invaluable. By analyzing historical weather data, energy output records, and real-time weather information, these models can predict the availability of solar and wind energy with remarkable accuracy. For instance, a neural network model can be trained on years of weather and solar irradiance data to forecast solar power generation. Similarly, wind energy output can be predicted by analyzing patterns in historical wind speed and direction data. These predictions are crucial for planning the electrolysis process, ensuring that green hydrogen production is optimized for the available renewable energy. But the application of machine learning extends beyond just forecasting. It also involves optimizing the energy mix. By analyzing data from various renewable sources, machine learning algorithms can suggest the most efficient energy mix for a given period, considering factors like weather conditions, energy demand, and production costs. The impact of accurate forecasting and optimization is significant. It leads to more efficient use of resources, reduces the risk of energy wastage, and enhances the overall sustainability of green hydrogen projects. Furthermore, these predictions are invaluable for grid operators and policymakers, as they provide insights into the feasibility and reliability of relying on renewable sources for large-scale hydrogen production. Section 3. Techno-Economic Analysis in Green Hydrogen Projects. Moving to the third pillar of integrating data science and green hydrogen feasibility studies, we focus on the Techno-Economic Analysis, TEA. TEA is a critical component in assessing the viability of green hydrogen projects. It involves a detailed examination of technical aspects alongside economic factors, a domain where data science methods, particularly predictive analytics and cost modeling, play a pivotal role. The first step in TEA is understanding the technological landscape. This includes evaluating the efficiency of electrolyzers, the durability of infrastructure, and the advancements in renewable energy technologies. Machine learning models aid in analyzing trends and predicting future technological advancements, thereby helping in making informed decisions about technology selection and investment. Cost modeling is another crucial aspect. The aim here is to predict the capital and operational expenses involved in setting up and running a green hydrogen plant. This is where predictive analytics come into play. By analyzing data from existing projects, market trends, and supply chain dynamics, these models can forecast costs with a high degree of accuracy. This analysis is vital for budgeting, financial planning, and determining the price at which the produced hydrogen needs to be sold to be profitable. Moreover, scenario analysis, another facet of TE, leverages data science to simulate various scenarios. These scenarios might include changes in market conditions, technology costs, policy impacts, and environmental factors. By understanding the impact of these variables, stakeholders can prepare for different future states, making the project more resilient to change. Additionally, TE involves assessing the revenue streams. This includes predicting the demand for green hydrogen in various sectors like transportation, industrial processes, and energy storage. Predictive analytics helps in understanding market dynamics and forecasting future demand, a critical factor in ensuring the long-term profitability of the project. Section 4. Environmental Impact Assessment in Green Hydrogen Projects. The fourth key aspect of integrating data science in green hydrogen feasibility studies is the Environmental Impact Assessment, EIA. EIA is crucial in ensuring that green hydrogen projects are truly sustainable and environmentally friendly. In this context, data science plays a significant role in accurately assessing and predicting the environmental footprint of these projects. The primary focus of EIA in green hydrogen projects is to evaluate the carbon footprint. This involves calculating the emissions associated with every stage of the hydrogen production process, from the generation of electricity using renewable sources to the electrolysis process and eventual transportation and use of hydrogen. Data science models, particularly life cycle analysis, LCA, tools, are used to perform these calculations. These models take into account various factors such as the source of electricity, efficiency of electrolyzers, and transportation methods to provide a comprehensive view of the project's environmental impact. Another important aspect is assessing the impact on local ecosystems and water resources. Green hydrogen production, especially through electrolysis, requires significant amounts of water. Predictive models help in analyzing the sustainability of water usage, ensuring that the project does not adversely affect local water resources and ecosystems. These models can forecast water availability and demand in the project area, providing insights into long-term sustainability. Data science also aids in simulating the impact of various project scenarios on the environment. For example, how different electrolyzer technologies or changes in renewable energy sources might alter the environmental footprint. This scenario analysis is vital for making environmentally responsible decisions throughout the project lifecycle. Furthermore, EIA involves continuous monitoring of environmental parameters once the project is operational. Data science tools can be used to create real-time monitoring systems that track emissions, water usage, and other environmental impacts, ensuring ongoing compliance with environmental standards and regulations. Section 5. Policy and Regulatory Compliance Analysis in Green Hydrogen Projects. As we conclude the first part of our comprehensive look at integrating data science and green hydrogen feasibility studies, Section 5 focuses on the critical aspect of policy and regulatory compliance analysis. This section is pivotal in ensuring that green hydrogen projects not only meet current legal standards but are also prepared for future regulatory changes. The complexity of navigating the policy landscape in green hydrogen projects cannot be understated. These projects are subject to a wide array of regulations, encompassing environmental standards, energy regulations, and safety norms. Data science comes into play by providing tools and models that can efficiently navigate and analyze these complex regulatory frameworks. One of the primary applications of data science in this context is automated compliance checks. By leveraging machine learning algorithms, it's possible to create systems that automatically assess whether different aspects of a green hydrogen project meet the necessary legal and regulatory requirements. These systems can process vast amounts of regulatory text, interpret the relevant clauses, and apply them to various aspects of the project, from production to distribution and usage. Predictive analytics also plays a role in forecasting potential future changes in policies. By analyzing trends in legislation and regulatory shifts in the energy sector, data science models can predict possible future changes in regulations. This foresight is invaluable for long-term planning and risk management, ensuring that projects remain viable and compliant in the evolving policy landscape. Moreover, data science facilitates the analysis of policy impacts on project economics. By simulating various regulatory scenarios, stakeholders can understand how changes in policies might affect the cost-effectiveness and feasibility of their projects. This helps in making informed decisions and adapting strategies to align with potential regulatory changes. In summary, policy and regulatory compliance analysis, enhanced by data science techniques, is a cornerstone in the feasibility studies of green hydrogen projects. It ensures that projects are not only compliant with current regulations but are also robust and adaptable enough to withstand future policy shifts. As we wrap up this section, stay tuned for Part 2, where we will cover the remaining aspects of integrating machine learning and data science in green hydrogen feasibility studies, further exploring how these technologies are shaping the future of sustainable energy. Thank you for choosing ReneEnergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at ReneEnergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.